Okay, my name is Schmit, and I had dye-sensitized solar cells. So just basics of solar cells. So you have a dye that is covalently bonded to a oxide semiconductor, typically titanium dioxide, which is usually bonded to a transparent electrode. And then the oxide semiconductor and the dyes are usually submerged in an electrolyte, typically iodide ions and triiodide. Um, So when the light hits the dye, it causes the photoexcitation of the electrons, and um, once the electrons are photoexcited, they can transfer to the oxide semiconductor, and then they pass through there to the transparent electrode through the external circuit back to the counter electrode, which then facilitates the redox reaction between the iodide ions and triiodide, which then provides an electron back to the dye, essentially regenerating it, allowing it to undergo photoexcitation again and transfer another electron to the semiconductor. So a major problem with dye-sensitized solar cells is their efficiency. They have other problems like stability and expensive components, but the efficiency is the one that we're looking at here. And so the question is, how does increasing the initial momentum of the electron affect the efficiency of the dye-sensitized solar cell? And my hypothesis was that as the initial momentum increases, the rate of electron transfer will also increase, thus increasing the efficiency. So MATLAB code was used for all this. Kinetic energy of the electron can just be described as momentum squared over 2m. Hamiltonian, the momentum operator squared over 2m plus the potential, the evolution operator, and then the propagation of the Gaussian wave packet. So here are the eigenstates. This square well to the left indicates the dye and its eigenstate. And then you have these 5 deeper wells indicating the titanium dioxide. So a probability distribution. So initially, all the electrons will be focused on the dye. The P naught is the initial momentum. X naught is the initial position of the dye, which you can see is centered around 35. And then you have the X var, which is the width of the well for the dye. And then I apologize, I could not get the videos to why. Apologies about that. So at the initial momentum 0, you'll see that a majority of all of the electrons are going to stay focused on the dye, and then you can see slight waves over the titanium dioxide semiconductor, showing that there is still a minor transfer of electrons between the dye and the semiconductor. And then compared to the initial momentum of 1, you can see that the electrons transfer much more freely and will pass to the titanium dioxide. And then you can think of to the right of titanium dioxide as it going out through the external circuit, and then the left being coming back through to the platinum cathode, and then facilitating the regeneration of the dye. Here just illustrates the probability of the electrons being found outside of the dye over time. So at the initial momentum of 0, you see that the max probability of finding an electron outside the dye is only 0.009 or 0.9%, compared to P naught of 1, which has a max probability of roughly 0.58, showing that increasing momentum does increase the electron transfer. And then this shows just the electron density. So 40 to 30 essentially indicates the dye, the electrons within the dye. So at the initial momentum 0, you can see that they're all focused within the dye. And then at initial 1, you can see that there is initially a higher density of electrons within the dye, and they very quickly disperse throughout the cell, and they transfer to the dioxide semiconductor. And then here you can see to the left, you can see these 5 pairs of darker lines, and these will indicate the these represent like the 5 wells for the titanium dioxide. And then in conclusion, so all the data supported that increasing the initial momentum increases the electron transfer, thus increasing the efficiency of the cell. And then once the electron's kinetic energy overcomes the barrier energy, it can transfer over to the oxide semiconductor. And then questions. So before any questions are asked, there was a question asked to me about, is the initial momentum related to temperature? They are both can be used to describe kinetic energy. So momentum squared over 2m describes the kinetic energy of a particle, or the electron, and then temperature is the average kinetic energy of the particles within the material. So yes, they are related, and increasing temperature theoretically would increase the initial momentum of the particles, but in the case of dye-sensitized solar cells, it is not a viable option as of now to increase the efficiency due to the electrolytes becoming unstable at temperature extremes like high temperatures and low temperatures. And then that's it.
Okay, please join me in thanking Connor presentation on the hot topic of the research.